Now that we see why poker chips are conserved, let's move on to see why momentum is conserved. And I think a great example of this is what we see in Mop 74, where we have the father and daughter on roller skates. Initially, they're both not moving, and then she pushes on the dad, and they both going off. They both go off in their own respective direction. She goes to the left, and he goes to the right. So let's see. He goes forward and she goes backwards. Now, why? Well, first of all, will momentum be conserved in this case? And I'm going to suggest that the answer is yes, because I'm going to say, well, her momentum won't be conserved and his momentum won't be conserved, but the father-daughter, the momentum of the father-daughter system will be conserved because, as we've already explained, the sum of all the external forces, gravity down and normal force up, adds up to zero. Friction is negligible, and we're not looking at some massive amount of time. We're just going to look at from right before the push off to right after the push off is momentum conserved. So whatever friction force there is small, the time is short, so it's negligible. Any impulse from friction is just way tiny compared to what the daughter and father are doing to each other. So their momentums are going to change, but the overall momentum of the system will be conserved. And what is the initial momentum of the system? I think it's pretty easy to see that since nothing is moving, then the initial momentum of the father-daughter system is zero. Well, what conservation of momentum says is, hey, even after they push off and she's going to the left and he's going to the right, and each one of them has non-zero momentum, that the overall momentum of the system after the push off, which would be P system prime, is still going to be zero. And this doesn't matter whether it was a tiny little push or a big push or anything in between. There's no way around this, and it really comes right from Newton's third law. So let's look at a force versus time graph of the force of the daughter on the father and his force back, because we know about Newton's third law. Let's say that this is the force of D on F. And that means, of course, that there's going to be an impulse from the daughter to the father. This is the force, and I'll just draw it in blue, I guess. And so the area is going to be the impulse on, let's make it not D for dad, but F for father, because we got already D for daughter. So he's going to have an impulse, his momentum is going to change, and he's going to move off to the right with a certain amount of momentum that's going to be equal to this area. But of course, Newton's third law says, hey, whatever daughter does to father, father's going to do back, and you know what I'm trying to do, even if it doesn't look very pretty. And so this is the force of the father back on the daughter. And that has its own impulse associated with it. And I think you see, and this is covered nicely in Mop 74, I think, is, let's see, what color? Let's go black. And so the area here is the impulse on the daughter. And you can see that whatever impulse the father got, the daughter got exactly the same impulse, but in the opposite direction. So let's just think about what the net impulse would be on the system as a whole, and then we can also think about what the impulse, the change in momentum would be. So let's think about impulse first. So the net impulse on the father-daughter system, well, there's nowhere, it's going to be zero because J on father is going to be exactly equal to J, not F, but J on the daughter. And if we think about the momentum of our system, the change in momentum of our system is going to be, well, we're just going to add up the change in momentum of the daughter plus the change in momentum of the father. And this is exactly equal to this, except it's minus. So if her momentum after the collision was, actually hers is going to be negative, his is going to be positive, but you get the idea. So just forget the, don't worry, what am I going to do? I'm going to change that. Get rid of that guy. Okay, so hers is going to be negative, his is going to be positive based on our diagram here. So let's suppose that after the collision, her momentum was negative 20 kilogram meters per second. Well, what's the dad's going to be? It's got to be plus 20 kilogram meters per second. So you see, it's going to add up to 0. Now let's look at one more example that's a little bit more complicated. Let's suppose that we have, and it can be in deep, deep space. Let's make it in deep, deep space. That I've got a box, and it's got 1,000,000 particles in it. And I'm actually only showing 4 of them. So they're numbered 1, 2, 3, 4, and the box itself is numbered 5. But just imagine there were 1,000,000 or 1,000,000,000 particles, all moving chaotically, all bumping into each other at various times, and many bumping into the wall. And what I'm going to say is that all of these millions of interactions over time cannot change the momentum of the system. Because, well, let's just look at one example, and you can see it's really essentially like the father-daughter system is. Let's suppose that 1 and 2 collide, and they exert forces on each other. And so what we're going to see is, what am I doing here? Okay, let's just go. So if they collide, so forget this. Okay, all right, there's that the momentum is going to change to be 0. So let's just look at 1 and 2. So let's just look at that one collision. What would be the momentum change of the entire system? Well, when 1 hits 2, its momentum is going to change. So there would be some change in object 1 momentum. But hopefully you can see that 2's momentum would be exactly the same. These are going to be exactly the same, except that 2's momentum change is going to be negative whatever 1's momentum change is. So it's going to add up to 0. So whether there's 2 particles or 1,000,000,000 particles, whether this is something that's very chaotic and crazy or whether it's incredibly simple, this will always be the result. And so this is why momentum is conserved let me just summarize that. So this is why the momentum of a system is conserved. It's supposed to be conserved when, and only when, the sum of all outside forces, which we'll call external forces, adds up to 0. Is truly 0 or adds up to 0. And it doesn't matter how complex or how simple the system. This is always the case. This is conservation of energy.